Welcome to Eyes Closed. 71% of this planet is covered in water. Not land, not ice, not cities or forests or deserts. Water, salt water specifically, the great connected body of ocean that wraps the earth in a single continuous system, divided by the continents that rise above its surface, but never truly separated, always connected beneath. If you flew over this planet and looked down, if you could see its home the way astronauts see it, a sphere floating in the dark, what would you see? Mostly is blue. The ocean, it is the defining feature of this world, the thing that makes it unlike anything else we have found in the universe so far. Liquid water in this quantity, at this temperature, maintained in this state for 4 billion years. These combinations of conditions that allowed life to begin and to persist and to eventually produce everything that exists on the surface of the land, including you lying here in the dark. Everything alive today came from the ocean, not a distant metaphorical sense, in the most literal biological sense. The first life appeared in the ocean. Every complex animal that has ever lived on land, every insect and reptile and mammal and bird is descended from creatures that once lived in the sea. The fish that first crawled onto land 450 million years ago was the ancestor of every land vertebrate that has existed since. You carry the ocean inside you, in the salt content of your blood, 0.9%, maintained precisely by your kidneys. A faint echo of the ancient sea in the fluid that surrounds your cells, in the way your embryonic development in the early weeks recapitulates stages of aquatic ancestry. The ocean is not just outside in some deep chemical sense, it is also inside. Tonight, we are going to follow it from the moment 4 billion years ago when water first condensed on the cooling surface of the young earth, to the deepest trenches in the Pacific where creatures live in permanent darkness under pressures that would crush steel. From the mechanism of the wave to the language of the whales, from the first sailors to navigate by stars, to the submarines that map the ocean floor, to the microplastics now found in the tissues of creatures living 6,000 meters below the surface. It is the biggest story we have told. Find your position. Take one slow breath in and let it out. The ocean is already moving. The ocean is 4 billion years old. The Earth itself formed from 4.5 billion years ago, condensing from the disk of glass and dust that surrounded the young sun, accumulating through the collision and gravitational capture of smaller bodies over millions of years. The early Earth was a violent place, hot, geologically active, constantly bombarded by asteroids and comets in the period known as late heavy bombardment. The water came from 2 sources. The first was volcanic outgassing. As the young Earth differentiated, the heavier materials sinking to form the core, the lighter materials rising to form the crust and mantle. The volcanic activity that accompanied this process releases enormous quantities of water vapor from the interior of the planet. This vapor, rising through volcanic vents and fissures, entered the early atmosphere. As the surface of the planet cooled, the temperature dropped below a boiling point of water. The water vapor in the atmosphere condensed. It began to rain. It rained for a very long time. The second source was extraterrestrial. The comets and asteroids that continued to bombard the young Earth carried ice, water ice, locked into the rocky and ice bodies of the outer solar system. As these objects struck the Earth, they vaporized, adding their water to the growing ocean. The question of exactly how much of the Earth's water came from each source, the volcanic outgassing versus the cometry and the asteroid delivery, is still actively debated by geochemists. The isotopic signatures of water from different sources differ in subtle ways, and measuring these differences in the Earth's water and in various meteoritic and cometary samples allows researchers to estimate the proportion. The current best estimate suggests that volcanic outgassing provides the majority of the Earth's water, with a significant contribution from asteroid impacts, particularly from a class of carbon-rich asteroids called carbonaceous chondrites, whose water has an isotopic signature similar to the one of the Earth's ocean. But the precise proportions matter less salt. 4 billion years ago, the Earth had an ocean, a single connected body of liquid water covering most of the planet's surface, deeper in some places than others, bounded by the young continents that were beginning their long, slow drift across the surface. The ocean has been here ever since, through the formations of the first continent, through the evolution of the first life, through 5 mass extinctions that each erased the majority of species on Earth, through the glacial periods when ice sheets covered vast proportions of the land surface and sea levels dropped by over 100 meters, exposing land bridges that allowed species, including our own ancestors, to walk to continents that had not previously reached. Through all of it, the ocean was there, moving, cycling, carrying heat from the tropics toward the poles and cold water back towards the equator in the great ocean conveyor belt of the thermohaline circulation, absorbing carbon dioxide from the atmosphere, producing oxygen through the photosynthesis of countless billions of tiny phytoplanktons, regulating the climate of the planet in ways that make the surface of the Earth habitable for the kind of life that has evolved here. The ocean is not passive geography. It is an active participant in the planetary system. It is one of the mechanisms by which this planet maintains the condition for life. Seawater is not simply water with salt added. It is a complex chemical solution containing, in varying concentrations, almost every element in the periodic table. The dominant components are water, H2O, approximately 96.5% by weight, and sodium chloride, common salt, which makes up about 77% of the dissolved materials. But alongside the sodium and chloride ions are magnesium, calcium, potassium, sulfate, bicarbonate, bromide, and traces of dozens of other elements. Gold is dissolved in seawater. There is an estimated 20 million tons of gold in the world's ocean, roughly the same amount as have ever been mined from the Earth. The concentration is vanishingly small, about 13 parts per trillion, which is why extracting it has never been economically feasible despite many attempts, but it is there. The salt in the ocean has been accumulating for billions of years through a simple process. Rivers erode minerals from the rocks of the continents and carry them dissolved to the sea. The sea loses water by evaporation, but not the dissolved minerals, which remain and gradually concentrate. Over geological time, as river after river delivered its dissolved cargo, the ocean has become saltier. This process has not been continuous or simple. There have been periods when large quantities of salt were removed from the ocean by evaporation in shallow inland seas, forming the great salt deposits found in rocks across the world. The vast salt deposits of the American Midwest, the salt mines of Poland, the Himalayan pink salt formed from an ancient sea that existed before the mountains were mountains. All of this are dried ocean. The salt content of the open ocean today is approximately 3.5%. This is the salinity that marine life has adapted to over hundreds of millions of years. Fish that live in the sea have body fluids with low salt concentration than the surrounding water. They are constantly losing water by osmosis through the gills and must drink continuously to replace it. Freshwater fish face the opposite problem. They must constantly pump out the water that enter by osmosis. The ocean's chemistry is not static. It changes slowly with time, and it varies across regions. The Arabian Sea is saltier than average because high evaporation in a relatively enclosed basin concentrates the salt. The Baltic Sea is much less salty because it receives large freshwater inputs from rivers and has still limited connections to the open ocean. The Dead Sea, technically a lake, not part of the ocean system, has a salinity 10 times that of the ocean because it has no outlets and evaporation is intense. The ocean is a single connected system, but within that system, the chemistry varies, the temperature varies, the biology varies. It is not one thing, but many things, all in dynamic relationship with each other. The ocean is never still. On the surface, wind drives waves at every scale, from the tiny riplets that form in a light breeze to the enormous swells generated by great storms in the middle of open ocean. The surface is in constant motion. A wave is not water moving forward. This is the most counterintuitive fact about waves, and it's worth sitting with. When a wave passes through open water, the water molecules do not travel with the wave. They move in circles, up and forward as a wave crest approaches, down and backwards as the through follows, and end up after the wave have passed approximately where they started. The wave is a shape moving through the water, energy in motion, not material in motion. You can see this with a floating object in open water, a buoy, a piece of driftwood, a duck. As a wave passes, the objects bob up and down and slightly forward and back. It does not travel with the wave. The wave passes through it. Ocean swells, the long, smooth, regular waves that arrive at beaches from storms far out to sea are generated by wind over a fetch of open water. The longer the fetch and the stronger the wind, and the longer the wind blows, the larger the waves that build. A major southern ocean storm can generate swells that travel 6,000 or 8,000 kilometers across the Pacific, arriving eventually at beaches in California or Japan as gentle, regular, rounded waves, all trace of the original violence of the creation, smoothed away by the thousands of miles of travel. A wave on a beach in New Zealand may have begun as wind over the North Atlantic. Energy transferred from air to water, traveling across an ocean, finally spending itself on a shore it will never leave. Below the surface, driven by differences in temperature and salinity, the ocean moves more slowly, but on a far larger scale. Cold water is denser than warm water. Salty water is denser than fresh water. Dense water sinks. This creates a slow vertical circulation in the ocean. The thermohaline circulation, or what oceanographers sometimes call the global ocean conveyor belt. In the North Atlantic, warm surface water flows northward from the tropics. The Gulf Stream, which keeps Western Europe warmer than its latitude would otherwise allow. As this warm water moves north, it cools. It also becomes saltier through evaporation. Cold and salty means dense. The water sinks slowly over the Labrador Sea and near Greenland and Iceland. Dense water descending to the ocean floor. This deep, cold, dense water flows southwards along the ocean floor, across the Atlantic, around the tip of Africa, through the Indian Ocean into the Pacific. In the Pacific, it gradually warms and rises, completing a circuit that takes roughly 1,000 years from the sinking in the North Atlantic to the rising in the North Pacific. 1,000 years, the water that is sinking into the deep ocean today in the North Atlantic will complete its journey and rise to the surface in the Pacific in the year 3000 and something. The ocean keeps time in ways that human life cannot easily comprehend. The ocean is divided into zones by death and by light. The uppermost zone, from the surface down to about 200 meters, is the volcanic zone, the sunlit zone. This is where light penetrates sufficiently for photosynthesis to occur, and it is where most of the ocean's biology activity takes place. In the volcanic zone, the foundation of the marine food web is phytoplankton. Phytoplankton, a microscopic photosynthetic organism. Some bacteria, some single-celled algae, some more complex protists that drift in the surface waters and convert sunlight and carbon dioxide into organic matter. They are so small that billions of them can fit in a cubic meter of water. They are so numerous that they form the base of virtually all marine food chains and are responsible for approximately half of photosynthesis on Earth. Half of the oxygen in every breath you take was produced by phytoplankton. They are invisible to the naked eye individually, but in large enough concentrations, they color the water green or brownish gray, or in the case of certain species, a brilliant blue-green that glows with bioluminescence at night, the waves breaking in curtains of cold blue fire. Phytoplankton blooms. The rapid multiplication of phytoplankton in conditions of abundant light and nutrients are large enough to be visible from space. Satellite images of the North Atlantic in spring shows great swirling patterns of color as the phytoplankton respond to the lengthening days, blooming in hundreds of thousands of square kilometers of ocean. The zooplankton graze on the phytoplankton. The small fish eat the zooplankton. The larger fish eat the small fish. The seabirds and the tuna and the whales eat the larger fish. The phytoplankton, invisible and innumerable, are the foundation of everything. At the surface of the volcanic zone, In the very top few millimeters of the ocean, where the water meets the air, lives one of the strangest communities in the marine world. The Houston is the community of organisms that live on or in the sea surface beyond the thin boundary layer between the ocean and atmosphere. It includes the Portuguese man OR, which is not a single organism, but a colony of specialized organisms, some forming the iridescent blue flow that rides the wind, others hanging below with tentacles that extend 40 meters. It includes sea skaters, insects, remarkably, that live their entire lives on the open ocean surface. It includes the violet sea snails, which creatures a raft of trapped bubbles from its own mucus and hangs below the surface, feeding on the man-made environment. A whole world in the top few millimeters of the ocean, a community of organisms adapted to the precarious boundary between the sea and the sky. Below 200 meters, the light fails. Not immediately. The transition is gradual. Between 200 and 1,000 meters, sunlight penetrates, but not enough for photosynthesis. This is the mesopelagic zone, the twilight zone. Here, the biology becomes stranger. The organisms of the twilight zone have adapted to low light, cold temperatures, and the challenge of finding food in a region where phytoplankton cannot grow. Many are transparent, their tissue offering nothing for predators to detect visually in the dim water. Others are counted shaded, dark on top, light below, so they are difficult to distinguish from the dim light above when seen from below. Many produce their own light. Bioluminescence, the biological production of cold light through chemical reaction, is so common in the twilight zone that some researchers estimate that the majority of organisms living between 200 and 1,000 meters are capable of producing light. The light produced for various purposes: to attract prey, the anglerfish encountered first in shallow water stories, but most at home in the deep, dangling its bioluminescence lure like a fishing line in the dark, to communicate with potential mates using specific patterns of flashing that identify the individual to others of its kind, to confuse predators. Some squid eject a cloud of bioluminescence ink rather than a dark ink of shallow water species, creating a flash of light that momentarily blinds and disorients an attacker while the squid escapes in the confusion. Every night, the organisms of the twilight zone migrate upwards. This daily vertical migration, one of the largest animal movements on Earth, involves billions of animals, from tiny shrimps to Latin fish to squid, moving up towards the surface each night to feed on the phytoplankton and zooplankton of the sunlit zone, then descending again before dawn to hide from visual predators in the deeper, darker water. The signal that triggers the migration is light. As the sun sets and the light at the surface diminishes, the animals begin their ascent. As dawn approaches and the light returns, they descend again. This migration carries enormous quantities of carbon from the surface to the deep. The animals feed on carbon-rich food at the surface, then descend and excrete or die and sink, carrying the carbon with them. This biological pump, the downward transport of carbon from the surface to the deep ocean, is one of the mechanisms by which the ocean absorbs carbon dioxide from the atmospheres and sequesters it in the deep. The daily migrations of billions of small animals, invisible and unremarked, is playing a role in regulating the carbon cycle and therefore the climate of the planet. Below 1,000 meters, there is no light at all. None. Absolute darkness. Not the darkness of a room with the lights off, which still contains some photons from outside. The absolute darkness of a place where no sunlight has ever penetrated, where the only light is biological, the intermittent, purposeful glow of bioluminescent organisms, the deep ocean, the bathypelagic zone, from 1 to 4,000 meters, and the abyssopelagic zone below that is cold. The temperature at depth is typically between 1 and 4 degrees Celsius, just above freezing. The pressure is crushing. At 4,000 meters, the pressure is 400 times atmospheric pressure, 400 times the pressure you experience on this surface. In this environment of cold and dark and crushing pressure, life exists. Abundant life, strange life, life so different from the organisms of the sunlit world that it required the invention of new categories to describe. The anglerfish of the deep ocean are more extreme versions of their shallower relatives. The females larger, carry a bioluminescence lure projecting from the top of the head. The males, tiny in comparison, spend their brief independent lives searching for a female by detecting a specific bioluminescent signal. When a male finds a female, he bites her and does not let go. His tissue fills with holes. His circulatory systems connect to hers. He gradually loses his own organs, becoming eventually little more than a sperm-producing appendage attached to the female body. A male anglerfish that has found a mate has found everything it will ever have. It will spend the rest of its life attached to that one female in the dark at 4,000 meters below the surface. The giant squid is the largest invertebrate on Earth. It can reach 15 meters in length. It has eyes the size of dinner plates, the largest eyes of any living animal, adapted to detect the bioluminescent flashes of predators and prey in the deep water. For most of human history, the giant squid was known only from the tentacles and beaks found in the stomachs of sperm whales and from occasional strandings of dead or dying individuals on beaches. It had never been photographed alive in its natural habitat. In 2004, Japanese researchers photographed a live giant squid for the first time at a depth of 900 meters in the Pacific Ocean. In 2006, a small squid was brought to the surface alive, briefly, and filmed before it died from the pressure change. The largest animal habitat on Earth, the deep ocean, was essentially unphotographed until the 21st century. We know less about the deep ocean than we know about the surface of the moon. The floor of the ocean is not flat. This was not understood until the 20th century, before systemic ocean floor mapping, which required the development of sonar technology. After the First World War, the seafloor was assumed to be a featureless plane, like the floor of a bowl. It is not. The ocean floor has mountains and valleys, plains and ridges, trenches and plateaus. The topography is as varied as the surface of the continents, more so in some respects, because the geological processes that shape the ocean floors are different from those that shape the land. The most dramatic feature of the ocean floor in the mid-ocean ridge system, a continuous chain of underwater mountain that runs through every ocean basin, totaling approximately 65,000 kilometers in length. The mid-ocean ridges are where new ocean floor is created. Molten rocks from the mantle rises through the ridges, cools, and solidifies, forming new ocean floor that slowly spreads outward from the ridge in both directions. This is the mechanism of plate tectonics. The ocean floor is continuously created at the mid-ocean ridges and continuously destroyed at the subduction zones where ocean floor dives beneath continental plates. The oldest ocean floor is less than 200 billion years old, young by geological standards, because older ocean floor has been subducted and returned to the mantle. The continents are carried along on the moving ocean floor like passengers on a conveyor belt. The deepest point in the ocean, the deepest point in the entire surface of the earth, is the Challenger's Deep in the Mariana Trench in the Western Pacific. It reaches approximately 10,935 meters below sea level. If you place Mount Everest in the Challenger Deep, its summit will still be over 2 kilometers below the surface. The pressure at the bottom of the Challenger Deep is approximately 1,100 times atmospheric pressure. The temperature is just above freezing. It is completely dark, and yet life. When James Cameron descended to the bottom of the Challenger Deep in 2012, only the third person ever to do so, and the first to do it alone. He found sediment and bacterial mats and small invertebrates. Life at the bottom of the world's deepest point. Life has found a way into every environment on Earth where liquid water exists and some energy source is available. The deep ocean floor is no exception. In 1977, a research submersible called Alvin descended to the floor of the Pacific Ocean near the Galapagos Islands and found something that overturned one of the foundational assumptions of biology. Life without sunlight. At hydrothermal vents, cracks in the ocean floor where seawater percolates into the crust, is superheated by the magma below and returns to the ocean floor loaded with dissolved minerals. Communities of organisms were living and thriving in complete darkness at temperatures near or above boiling, in water rich with hydrogen sulfide, a toxic gas that would kill most organisms instantly. The foundations of these communities was not sunlight, it was chemistry, chemosynthetic bacteria. Bacteria that derive their energy from chemical reactions rather than from photosynthesis form the base of the food web. They use the energy from the oxidation of hydrogen sulfide to fix carbon dioxide into organic compounds. The same end result is photosynthesis, but by a completely different route. Around these bacterial communities live organisms of extraordinary strangeness. Giant tuberworms, Riftia pacifica, up to 2 meters long, brilliant red, anchored to the rocks around the vents, with no mouth and no digestive systems. They live entirely by hosting chemosynthetic bacteria in a specialized organ, the trophosim, that occupies most of their body. The worm provides the bacteria with hydrogen sulfide and oxygen. The bacteria provide the worm with the organic compound it needs to live. A completely obligate symbiosis. Giant clams, white and pale, clustered around the vents. Blind shrimp with light-sensing tissues on their backs. Pale crabs peeking through the bacterial mats. The discovery of hydrothermal vent communities forced a fundamental revision of our understanding of life. Before 1977, it was assumed that all life on Earth ultimately depended on sunlight, that the energy in every food chain traced back to photosynthesis. This is still true for the vast majority of life, but it is not true for vent communities. They are powered by the heat of the Earth's interior, not by the sun. This discovery has profound implications for the search of life elsewhere in the solar system. Europa, one of Jupiter's moons, is thought to have a liquid water ocean beneath its icy surface, heated by tidal forces from Jupiter's gravity. Enceladus, a moon of Saturn, vents water vapor from hydrothermal activity into space. If life can exist in dark, hot, chemically extreme ocean floor environments on Earth, the possibility of life in the subsurface oceans of these moons becomes much harder to dismiss. The deep ocean vent and its strange living community point outwards into the solar system. The largest animals that have lived on Earth are alive right now in the ocean. The blue whale, Balaenoptera musculus, can reach 30 meters in length and 170 tons. It is larger than any dinosaur that has ever been found, larger than anything that has ever walked on land. The heart of a blue whale is the size of a small car. Its heartbeat can be detected by sensors placed miles away. It's called a deep resonant pulse below the range of human hearing. It's the loudest sound produced by any animal and can travel thousands of kilometers through the ocean. The blue whale feeds almost exclusively on krill, tiny crustaceans a few centimeters long, the largest animal on Earth, sustained by some of the smallest. It eats 3 to 4 tons of krill per day in its summer feeding seasons. Whales breathe air. They are mammals. Their ancestors walked on land. The ancestor of modern whales were 4-legged land mammals living in South Asia approximately 50 million years ago. Animals that look something like small deer or large dogs that spend increasingly amounts of time in water that gradually evolved over millions of years of natural selection into fully aquatic animals. The evolutionary transition from land mammal to whale is one of the best documented in the fossil record. We have a series of intermediate forms: Pachycetus, a dog-sized land mammal with whale-like ear bones that lived 50 million years ago. Ambryocetus, a 4-legged animal that could walk on land and swim in water. Protocetus, with reduced in length and a more streamlined body. And then, 40 million years ago, Basilosaurus, a fully aquatic animal with tiny vestigial limbs and a body 15 meters long. 15 billion years from land mammal to blue whale. The return to the ocean that began in those shallow coastal water of ancient South Asia. Whales sing the song of humpback whales, the long, complex, ever-changing sequences of moans and cries and whistles that male humpbacks produce during their winter breeding season are the most complex acoustic performances of any non-human animal. A humpback song lasts between 10 and 30 minutes and is repeated, sometimes for hours, without pause. The song changes gradually over the season and across years. New elements are introduced, old elements are dropped, and the change spread through the population as if by fashion, with whales in adjacent areas adopting with new elements and carrying them further. A song that begins in the waters around Australia will, over the course of a decade, spread westward across the Indian Ocean to South Africa. Cultural transmission in Wales. Song as culture, spreading across an ocean. Human beings have been going to sea for at least 50,000 years. The first inhabitants of Australia arrived approximately 65,000 years ago, which required crossing open ocean. No land route existed then or has existed since. Whatever boats or rafts those first Australians used, they were capable of open ocean crossing in conditions that would be challenging in a modern vessel. By 40,000 years ago, humans had reached islands across the Western Pacific. By 3,000 years ago, the Polynesian people were navigating the open Pacific in double-hulled canoes, finding and settling islands across an ocean covering a third of the Earth's surface, navigating by stars and swells and behaviors of seabird. Polynesian navigation without instruments is one of the most sophisticated cognitive achievements in human prehistory. Navigators memorized the rising and settling points of hundreds of stars. They read the shape of ocean swells, their directions, their period, the way different swells from different sources interact and create patterns that an experienced navigator can feel through the hull of a canoe. They track the behavior of seabirds, which species flying in which direction at what time of the day, as indicators of nearby land. They found Hawaii, they found New Zealand, they found every island in the Pacific that is large enough to support human life. Without a compass, without charts, without any instrument beyond the trained human body and its capacity to read the ocean. European sailors, when they began their own ocean crossings in the 15th century, had magnetic compasses and later chronometers and sextants. They had tools. The Polynesian navigators had knowledge. The ocean has always been both barrier and highway. It separates, makes islands of continents, keeps population apart for long enough to differentiate into different species. But it also connects, provides the route that determined navigators use to reach what lies beyond. The ocean is not the end of the world, it is the middle of it. The ocean is moving right now. While you lie here, while you breathe, while the house settles around you, while the night deepens, the ocean is in motion. The thermohaline circulation is carrying deep, cold water from the North Atlantic towards the floor of the Pacific, a journey of 1,000 years that is happening at this moment, as it has been happening continuously for millions of years. The phytoplankton in the surface waters of every ocean are doing this slow work. Even now, in whatever hemisphere is experiencing daylight, photosynthesizing, producing oxygen, fixing carbon, forming the base of the food web that supports every marine creature and contributes to every breath taken on land. In the deep ocean, at 3,000 meters, in complete darkness, a creature is hunting that no human eye has ever seen. It carries its own light with it. The light moves through the dark water, looking for something to eat, finding or not finding, continuing. On a beach somewhere, on many beaches all around the world, waves are coming in. The sound is the same sound it has always been. The irregular percussions of water meeting land, the hiss of the treating wave of a storm of sand, the pause before the next, the rhythm that is never quite a rhythm, because no two waves are ever exactly the same. People sleep near that sound. They find it easier to sleep near the ocean than away from it. The sound of the ocean, the specific acoustic texture of waves, reduces the activity of the part of the brain that monitors for threat. The nervous system recognizes it as safe, as the sound of a good place to be. You are not on a beach tonight, but the ocean is out there somewhere. The same water that has been on this planet for 4 billion years. The water that was breathed out by the first living things. The water that the first fish swam in. The water that the ancestors of whales returned to 50 million years ago, choosing the ocean again. It is out there, moving, ancient, indifferent, patient, and you are here, warm, still inside. The ocean will be moving in the morning when you wake. It was moving the night before you were born. It will be moving on a night long after you are born. There is something in this that is not frightening if you let it settle. Something old and continuous and entirely untroubled by the passage of any single night. Let your breathing slow. Let the dark be wide. The ocean keeps moving and you can rest. And that is where we will leave it tonight. You came here to rest, and I hope that is exactly what you are doing right now, or close to it, somewhere in that warm, quiet place between knowing and not knowing, between the story